They measure the distance to a star. How do they measure the distance to another galaxy? These are tough things to figure out. And so that's what we're going to spend some time on today. And one of the main ways that they measure distance is called parallax. So do me a favor. Put your finger in front of your face like this and close one eye. And note where the finger is. You got to hold it up. Note where the finger is in relation to the background wall. Okay? And then leave the finger in the same spot, but open the other eye. And you can see, if you do that back and forth, the finger jumps from one spot to another. Do you notice that? Adrian, you're not doing it. Isn't that cool how it jumps? Isn't that impressive? It's a magic jumping finger. Okay? Now do me a favor. Now look up here at my finger. And do the same thing, one eye to another. Do you notice how far it jumps? Which jumps farther? The finger when it's in front of your face? Which appears to move farther compared to the background? Or the finger up here? The one near your face, right? And what happens is your brain, when it sees any object, does a calculation. Because your brain is getting a picture from both eyes. And if you see an object just sitting here in space, like I'm looking at this desk, my brain sees it with the left eye, and it sees it with the right eye, and my brain immediately notes how far that shifts, what the difference in the shift is with the picture coming from each eye, and my brain can figure out the distance from that. My brain knows that if it's shifting real far, if the two pictures coming from each eye are very different, that means it is very close. And if the shift from each eye is not much at all, that means it's very far. And the brain knows exactly how much shift is how far. And so the brain can immediately figure out the distance to any object. And that is good for us, especially for our primate ancestors that were swinging around in trees, jumping from branch to branch. You got to know exactly how far the branch is in order to be able to jump and catch it. Does this make sense? Are we good? Give me a thumbs up. There you go. So, you can tell distance if you have two pictures taken from different places of an object by comparing it to the background. And you can see, look, there's the finger in front of the tree. If with the right eye open, and if the left eye is open, the finger is not quite in front of the tree. So we know that finger is somewhat close to the person. Here's another way of looking at it. Here is a star. From viewpoint A, the star has the blue background. And here's how it looks from viewpoint A. The star is in front of the blue background. From viewpoint B, the star is in front of the red background. So, from viewpoint A, the star is toward the right, and from viewpoint B, the star is toward the left. Y'all with me here? So, here's another way of looking at it. Do you notice how far the red block and the gray block there are moving? I guess that's a blue block. Is that blue or gray? That one right there. What color is that? What would y'all say?
I would say it's gray.
Gray? Okay, so notice how far the gray block moves, but notice the blocks in the back aren't moving nearly as much. See the green block and the blue block in the very back? They don't seem to move as much because they're farther away. It's the same sort of idea. Is this making sense? And we know that the round ball and the yellow block are kind of in the middle because they're moving an in-between amount. So you can figure based on the movements of these objects what's close and what's far. Make sense? Something close to you moves more, something far away moves less compared to the background. This is the idea that we call parallax. So how do we do this with astronomical objects? Well, we know that the Earth moves around the Sun. So let me get my models out. And let's say this is the Earth. This will be the Earth, and this will be the Sun. Now, what you need whenever you're figuring out the distance to a far-off object, you need pictures from two different places. So one way you can do that is take a photograph. Let's say here's our observatory in Atlanta. And the Earth turns, right? So we can take a picture when the Earth is right here of a far-off star. And another picture later in the day after the Earth turns, the observatory is right here now, and we can take a picture. And so we have two baselines. I mean, we have a long baseline here. We took a picture from here and a picture from here later in the day. Does that make sense? And we can see the difference between those 2 points, and we can see if the object moves. If you were to take a picture of the moon compared to the background stars and took the picture here and then here, does anyone know what that distance is between the distance across the Earth? Do you know what the Earth's diameter is? Anyone know?
I know the circumference.
I think it's about 8,000 miles, but let me check. Siri, what is the Earth's diameter?
The diameter of the Earth is about 7,913 miles.
There you go. So, 8,000 miles. So it's about 8,000 miles difference. So that's kind of like having two eyes that are spread apart and taking a picture with one eye here and one eye here, and you see how much the moon shifts, and you can calculate how far the moon is by how much it shifts compared to the background stars. Isn't that cool? However, we can do even better than that. We know that the Earth goes around the Sun, right? The Earth goes around the Sun. Do y'all know that? What's the distance from the Earth to the Sun? Any idea?
Oh, it's 93 million miles.
93 million miles. And we have another name for that. 93 million miles is called 1 AU. 1 AU is 93 million miles. It's 1 AU to the Sun. As a matter of fact, the license plate on my car is 1 AU to Sun. Isn't that cool? That way I won't forget how far it is to the Sun. It's 1 AU. So the Earth is 1 AU from the Sun. So if we get a picture of a far-off star from here, and then 6 months later we wait and we take another picture from here, you might see some shift to that star. A close star shifts more than a far-off star compared to the background stars and galaxies that are way, way far away. Does that make sense? So here we see in this diagram, can you get this diagram on tape? Whoops. Here we see in this diagram, here's the Sun, here's the Earth. That distance there is 1 AU. And there's the Earth going around. And there's a nearby star. And there are far-off stars in the distance. And so from Earth, if we see this star with these far-off stars behind it, the star will appear as if it's between those two stars. And then 6 months later, when the Earth is on this side and we look at it, the star appears behind, between those two stars. So we know that that star has shifted a certain amount, and we can mathematically determine the distance to the star that way. So we call this angle that's produced, the angle that's produced right here between where the sun is. Notice we make a triangle here, and this is what we're about to do. We're about to go outside and do this outside. We're going to do it mathematically. We've created a triangle here. You see that triangle? And we have an angle here from the star to the Earth and the sun. So there's an angle there. That little angle is called the parallax angle. Okay? And think about that triangle that we have there. So if we know, here we make this triangle. Here's the Earth. This is the Earth. This is the sun. And this angle right here is called the parallax angle. And if you think about it, if that star is far away, that parallax angle is going to be real small. If that star is near, is this thing in the way?
Oh no, it's not in the way.
If that star is near, the parallax angle will be more. So the farther away the star, the smaller the parallax angle. Now, have y'all taken trig before? Trigonometry? Yes on trig? Yes on trig? No on trig? Have you ever heard of sine and cosine and tangent? Y'all know that? So, think about it. We know this distance. What did you say this distance was?
93 million miles.
This is 1 AU, or 93 million miles. That's that distance. So if you know that distance and you know this parallax angle, let's say that parallax angle is 2 degrees. I don't know. We're just making something up. Okay? And this angle for stars and stuff is going to be way less than 2 degrees. But for the sake of argument here, we'll say 2 degrees. Yeah.
Mr. Sutter sent me in here. He said, do you have colored pencils we can borrow?
Yes. If you look in drawer 7 of any of these tables, there are colored pencils in it.
Thank you.
So, do y'all know how would we figure this line, this distance to the star? If this is a star, or some planet, or some satellite, or an asteroid, something you wanted to figure the distance to. Let's say it's an asteroid. An asteroid could give us a measurement of 2 degrees. So, if this is 93 million and that's 2 degrees, how long is that? Can we figure that out? How would you do it? Think about math.
Using the...
What do we call this line right here, from this angle? What do we call that line? Do y'all remember? I'll give you a hint. This one right here is called the hypotenuse.
Yeah.
This is the hypotenuse.
Is it opposite?
Yes. This line right here is called opposite. And what's this line right here called?
Adjacent.
Adjacent. Y'all remember this math? Math is fun. So, how do we find the adjacent? The adjacent, that's the line that will tell us the distance to the asteroid. How do we find the adjacent?
Tangent.
Do y'all remember SOHCAHTOA? Did y'all do that in math? Sine is the opposite over the hypotenuse. Cosine is the adjacent over the hypotenuse. And tangent is opposite over adjacent. So if we have this measurement, 2 degrees, the tangent of 2 degrees, is going to equal the opposite, 93 million miles, 93 million, over the adjacent, whatever the adjacent is. You can now figure for the adjacent. You want to do that? Siri, what's the tangent of 2 degrees?
Let me have a look. The answer is approximately 0.0349208.
0.0349208. So how do we find A? We take 93 million divided by that. You see? You want me to do it?
Yeah.
I got a calculator here. Let's turn it on its side so we can get a number this big. 93 million divided by 0.0349208. 2,663,000,000. So this is this distance right here. 2.7 billion miles. There we go. We got the distance to the asteroid just by knowing this parallax angle. How cool is that? You just find how much it shifts and figure out the angle for that amount of shift. The angle coming from the Earth for that amount of shift. That'll be your parallax angle. Now, have you ever heard the term parsec? You ever heard that term? A parsec is a unit of distance used in astronomy. A parsec means a parallax angle equal to 1 arc second. Now, what you have to understand is what an arc second is. Okay? So I'm going to explain to you what an arc second is. An arc second is not very much angle. It's just a little bit of angle. So let's think about the sky. Have y'all ever seen a contraption that looks like this? Don't worry about the straw and the weight. What is this right here? Say what this thing is, and I'll be happy.
A protractor.
A protractor. Have y'all seen a protractor before? Yes?
Yes.
So, this protractor, what does it measure?
Degrees.
It measures the degrees of the sky. Okay? And it goes from 0 degrees to 180 degrees. In other words, if you're going from this horizon to that horizon, you go through 180 degrees of sky. Does that make sense? If you were to go all the way around, it'd be 360 degrees. But just from this to there is 180. Okay? So imagine the entire sky broken up into 180 degrees. How much would 1 degree be? How much of the sky would 1 degree be? It'd be about, with my arms extended, maybe about that much. Imagine 1 degree, 2 degree, 3 degree, 4 degree. If I counted 180, I would go all the way through the sky. Does that make sense? Are y'all with me? So 1 degree of sky is about, hold your pinky up at arm's length. Hold it up to the sky. It's got to be at arm's length. It's about the width of your pinky. That's about 1 degree of sky. Okay? The width of your fist, that's about 5 degrees of sky. So 1 degree of sky is the width of your pinky. 5 degrees of sky is the width of your fist. Okay? You can always you can make measurements out there on your own at night. Make a guess for me. How many degrees of sky wide do you think the full moon is? Think about it with your finger and your fist. Would your fist cover the full moon? If so, the full moon is less than 4 degrees of sky, or 5 degrees of sky. Would your pinky cover the full moon? If so, the full moon is less than 1 degree. So I want you to guess right now. We only have 3 people in here for those who are watching at home. I want you to guess how big the full moon is in degrees of sky. We're going to have 3 guesses, and the closest guess wins a sticker. What's your guess?
7 degrees?
7 degrees. What's your guess?
3.
3 degrees. What's your guess?
5.
5 degrees. The winner... Sticker. This is so exciting. It's hard to get the sticker out, y'all. The winner of the sticker is Adrian. And y'all were all way too high. You know how big the full moon is? It's half a degree. It's half a degree. Hold your finger again at arm length and hold your pinky up. Do it again. And imagine half your pinky. That's all the full moon is. If you don't believe me, go look at the moon tonight. It's a gibbous moon right now. It's still pretty big. And try to cover it up with your pinky. And you'll see your pinky easily covers up the whole moon. The moon is about half a degree of sky. Can you believe that? Doesn't it seem bigger? Look how little your pinky is compared to the sky. Doesn't it seem bigger in your head? It's not. That's as big as it is. And it doesn't matter if it's on the horizon. Have you ever seen the pictures where the moon is real big on the horizon? Doesn't it seem like the moon is bigger when it's on the horizon? It's not. It's still half a degree. You can still cover it up with your pinky. Even when it never changes size. It looks big on the horizon. It looks smaller when it's up high. It's always about half a degree. Those are things your brain is doing to you. Little tricks your brain plays on you. Your brain makes you think the moon is bigger than it actually is. It's called an optical illusion. Have you ever heard of that before? We're learning so much here today. I can't believe it's only the 3 of us. So, imagine what 1 degree of sky is. Hold your pinky up one more time. I know you're getting tired of doing this. Imagine that's 1 degree. Now, 1 degree of sky is broken into what we call minutes. Minutes, so it goes degrees and then minutes. There are 60 minutes in a degree. So imagine taking your pinky and breaking it up into 60 equal slices, 60 equal divisions. That's how big a minute of arc angle is. 1 minute of sky is 1/60th of a degree. So we're talking just about a little bit of sky when we're talking about a minute of sky. Okay? Are y'all with me? Minutes, each minute can be broken down into what we call arc seconds. So we have degrees, and then we have arc minutes, and then we have what's called arc seconds. So a minute is 1/60th of a degree. A second is 1/60th of a minute. So we're talking about a really tiny amount of sky now. 1/60th of a minute, which is 1/60th of a degree. So a second is equal to 1/3600th of a degree. Is this making sense? An arc second is a really small amount. So, when we talk about a parsec, what is that? A parsec is a parallax angle equal to 1 arc second, to 1/3600th of the sky. So if this little angle here is really small angle, it only covers 1/3600th of a degree of the sky. And that's not 1/3600th of the sky, that's 1/3600th of 1 degree. If you multiply that times 180, it'd be 1/100,000th of the sky or something like that. Millionth, 1/1,000,000th of the sky. Just a little tiny bit of the sky. If we have this little tiny angle from the Earth, that means that thing's really far away because that angle is so small it takes a long time to spread out to get to 93 million miles. Are y'all with me? Ask a question if I've lost you there. So how far is a parsec? If something is far enough away where it's 1 arc second of the sky parallax angle, it's a parsec away. And we know from mathematics 1 parsec is equal to 3.3 light years. 3.3 light years. That's a parsec, 3.3 light years. So if something is so far away that it only shifts 1 arc second, if we take a picture of it here and we take a picture of it 6 months later, the shift is 1 arc second. That means it's 3.3 light years away. How far is 3.3 light years? Were you going to ask that? What were you going to ask?
If that is such a small little shift, how are they able to tell that it shifted?
They can still tell. A picture here and a picture there only shifts a little bit, but they can tell with their telescopes. They can see that little bit of shift. You wouldn't be able to detect it with the naked eye, but you could detect the shift with telescopes. They take a picture of stuff with telescopes. Yeah. Make sense? So if we see something shift 1 arc second, we know it's 3.3 light years away. So that distance, that's the amount of distance light can travel in 3.3 years. Light can go a long way in 3.3 years. Do y'all know how fast the speed of light is? The speed of light is 180,000 miles per second. That's the speed of light. That's how fast light travels. If I turn on a flashlight, it travels through the room at 180, the light does, at 180,000 miles every second. That's about 6 times around the world every second. That's pretty fast. Okay? More than that. It's about 7 times around the world in a second. 8 times around the world in a second. 7 or 8 times around the world in 1 second. That's fast. But of course, light isn't traveling in circles, light's traveling in a straight line. So imagine how far light could go in a year. If it can travel 180,000 miles in 1 second, think how far it could go in a year. Well, a parsec is equal to 3.3 light years. It could go 1 year, 2 years, 3 years. If light travels that long, it's gone a very long way, many trillions of miles. And that's how we measure astronomical distances, in light years and parsec. You'll hear the term parsec used a lot in the book, in our reading. It's 3.3 light years. The nearest star to us is called, does anyone know what it's called?
Ooh, it's like the Promethea Centauri.
No.
Beetlejuice.
Nope. Any idea? Nearest star is called Alpha Centauri. You ever heard of that? Alpha Centauri is the nearest star. It's 4.3 light years. So it's farther than a parsec away. 3.3 light years is 1 parsec. 6.6 light years would be 2 parsecs. So parsec is a measure of distance.
How far away is it, did you say?
4.3 light years. A little over 1 parsec. It's like 1.3 parsecs away. You understand all this about angles and stuff like that? Y'all got any questions? You want to go outside and do a little measurement? Do we got time? What's the time this period in? It's 11:15, isn't it? Yeah? Oh, yeah, let's go outside and do a measurement.